Hey, Prem.
Hey.
Can you hear me?
Yes.
Do you know how to? Yes. Do you know how to mute the phone?
*6.
*6.
Yep. No, I sent you an email.
Okay.
This one. Yeah. Let's give a few more minutes before we start. So before we start, did anyone had a chance to use this Spark program on any of your projects?
This is Mike in Tucson. I tried to use it on our one, but we don't have rectangular spaces. We've got some kind of spaces that the shapes don't really seem to work in the spot if they don't have a overall kind of three-sided shape. We've got a space that's down at say 9.4, but then it's got a high kind of 13-foot clear story on either side of the space, so the shape kind of becomes in section becomes a U shape, and yeah. I couldn't find out how in the Spot program to get that kind of space to work.
Now that would be difficult in Spot. The only space that's possible is a rectilinear space.
Yeah, so I can get the rectilinear space below the clear stories, but it's really hard to accurately get a space like that in Spot.
And volumetrically, I think it has to be a rectangle in section as well.
Yeah. So that would be the only downside for say like the specific projects that I was trying to work for today's thing, is that both of the projects don't have kind of straight rectangular spaces other than say a normal window, and we have some spaces that are kind of large open area kind of with clear stories that we were trying to get an idea of what the daylighting would be in there, but when you can't accurately do it, it kind of doesn't lend itself
that
to
is
that
the problem. I think as soon as we get into that level of complexity in design, we would have to move to some other programs such as AGA 32.
Yeah, okay. But I tried. It just didn't. It wouldn't work for the spaces we really wanted to try our daylighting on. So.
Okay. All right. Maybe we'll cover that on another training session to go over AGI sometimes.
Okay.
And I know, Casey, you did try your Denver office, seems like?
Yes, that's correct. I just kind of simplified our volume here, but I was able to model up our work area. And,
okay.
Definitely got an analysis out of it. I'm not quite sure if I understand what all it told me, but we can go through that here in a bit.
We can go over that today. How about anybody else? Did you have a chance to play with Spot? I would take that as a no. Okay. So hopefully, and again, I'm going to go through just one last item today. Please take the time to go through this and apply it on any of your projects. And as I mentioned in the email, you could even apply it on your house just to test it. Just take a living room or dining room or something, just test it out and see how it actually works. Okay. So I'm gonna start. So today we want to just go over visual comfort one more time fairly quickly, and then I'm going to ask Casey to share his example of the Denver office, and we can walk through what his experience and drawbacks and such. And then finally, I'll walk you through lighting and energy savings today. So just a very quick overview of visual comfort. So we looked at 6 key performance indicators, and we're talking about visual comfort, and we're using Spot as a program to evaluate visual comfort. And defining visual comfort, it's not only having adequate lights, but also balanced light and no glare. And we're using some of these metrics to measure visual comfort, daylighting autonomy, minimum and maximum daylighting autonomy. Just some examples, and we can go over this again when we get into spots. The balanced light, minimum daylighting autonomy is at least you should have 60% of your space meeting the daylighting requirements for your space. And as far as no discomfort glare, no more than 5% of the space can have 1% of maximum daylighting autonomy, which is 10 times your required foot candle. So within Spot, we have 6 steps, and we went through defining the project performance criteria and geometry input, and we went through site and usage last time, and also annual daylight performance. And today we're going to look at night light performance, photosensor location, and then try to figure out how to predict energy savings. Okay, so I'm going to turn this over to, do you have any questions before we turn this over to Casey? Anyone?
Prem, this is Kelly. How do you mute the phone?
Oh, *6.
*6, thank you.
Right, either *6 or *5.
Casey, I'm not sure how to do this, so I'm going to try something. Let's see. Casey, I'm giving you rights to be the presenter.
Okay. The dual monitors always. Do you guys see my spreadsheet?
Yep,
or do you see my email?
Outlook.
Oh, okay. There. All right. Well, here's the final kind of report that came out. Can I just back up and go back to the start, or will that ruin the calculations at all?
No, you can go all the way back, except for the first screen. So you should probably stop at the one more. Yep. You don't want to go back from there.
Okay. Let's see here. So yeah, I just kind of chose the general work area that we have here in Denver, and inputted the basic windows. The only exception I couldn't figure out, and I missed last time if you guys went over it, was if you can rotate the compass at all.
Yes, you can.
Okay.
Do you see that orientation box on the left?
Right here. So I should have rotated that. Okay.
Yeah.
Well, I will go through. I won't recalculate it right now.
Okay.
But essentially, I kind of came through. In Denver, we have kind of a general seating area where most of us sit, with some windows here on the east or northeast side. And then we have an outdoor patio with a big overhang. And then there's also some windows kind of at this point with another volume coming back. But for the purpose of this analysis, I just kind of simplified it down to this general work area. Modeled up the large opening we have here, and then our kind of 3 large window openings across the east side there. I did leave the reflectances pretty much standard. I didn't go into great detail on those on trying to look up. I mean, what guidance do you have there for trying to figure out the reflectance of carpet or, of a paint
I
swatch?
think it's mainly the walls and ceilings.
Okay.
So typically, if we have one of those off-white color that we have on the walls, it's typically 70%.
Okay.
But again, that depends on how much of sketches and things that are hanging on the wall. That'll alter that reflectiveness. So 50% is a good average, and take a look at what you have in that space. And if it's just pretty much blank walls, and if it's just a white paint on it, then I would suggest going to a 70%.
Okay.
And ceilings, typically the grids that we have, they range about 80%, so that's pretty normal.
Well, like I said, I'll leave this alone so it doesn't recalculate, but it's kind of what I used. Going through, set up the basic openings, and then left the transmittance at essentially full We do have window coverings, but for the majority of the day that they're not used at all.
Okay. But one question I have for you, Casey, is the windows are taller than the space?
They are. It's kind of odd. They the grid, ends about 6-8 inches from the wall, and the windows continue up another foot to 2 feet above that point. So,
for our daylighting purposes, I would consider trimming the window at the top of the ceiling, because
sure.
that's our enclosed volume for daylighting calculations.
Okay.
So you don't have to change it now, but I'm just as a tip.
Oh, very good. Yeah, essentially it'd just be a complete light shelf, so it would get cut off anyway.
Right.
Moving on to the next one. I went through, and essentially we have someone in here at least one day every weekend, so I considered the space occupied 6 days a week.
Okay.
And I just kind of simplified it down to the 7th and 14th, 21st day as being the unoccupied straight across, kind of throwing out the weekdays. I suppose I could have gotten more detailed and gone in and found that what holidays we don't work and whatnot, but
this is good enough for a study, I would think.
Sure. And then the site, they don't have Denver, so I just went with Boulder, being as close.
And while you were at it, I may want to just add that button right down below Spot Generic under Site Selection, Convert EPW file. That is something that you can also try. If your weather station is not available, for instance, if you don't have Denver, then you can go to that website from that tooltip that you're seeing and download the EPW file for Denver, because there's locations for almost 3,600 locations in the U.S., I think.
Perfect.
So you can download that and then save it somewhere in your desktop, and if you hit Convert EPW file, it'll open up that file, and it'll gather the weather data from that EPW file. EPW stands for Energy Plus Weather Data.
Okay.
Okay.
Very good. Then, moving forward, I guess I ran initial analysis with one zone.
Right.
And
this is the part that I will go through today, Casey.
Okay.
This is the night work plane illuminance, so this is strictly from the artificial light that we have. So I will go through this today.
Okay. Yeah, I just kind of modeled up. We have 3 rows of 5 columns of indirect lights, so I put them in and let this run. Then these were the daylight results.
So if you can change the design conditions on the left-hand side for equinox at 12 o'clock, you can kind of get an idea of how at different times you have different lighting in the space.
So here, what are we looking for? Do we want to be over 100%, or do we want to be less than 33?
Right. See, that's where we have to define what our daylighting goal is in the beginning. So on your on that geometry input that you had, based on the amount of windows, so it seems like you were able to cover almost 75% of your space with more than 40-foot candles. Assuming 40-foot candles is our design luminance that we want, right?
Correct.
So this is a very good daylighting scenario, but you can check the view report. Click the view report on the top. Yep. So if you click the view report, what does it say? It does say at the very bottom down here, if you see adequate annual quantity of daylight, but direct sunlight or exceedingly high daylight illuminance exists. So that's because of your east-facing glass without any protection.
Okay.
So the one way to check that is if you hit back on the top right-hand corner. So see at the very end of your east wall by that 39 length, you see 680 foot candles, 575, 410, blah, 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 right? So your normal design illuminance that you're required to have in that space is 40-foot candles. So we get glare if the amount of light is 10 times above your design illuminance. So if we're required to have 40-foot candles and if you have 400 plus, then that's the potential to cause glare, and that's what this program is telling you right now.
Very good. Now, the one condition we'd have here, we're in an urban site, of course, so we do have buildings across the block.
So that is
there's
true.
no way to account for that, correct? Like a vertical.
Nope, that's not at all. So that's when you have to get into AGI to be really precise, but to come up with some rule of thumb, you can check that out in SketchUp. Just draw these volumes, space them out as per design, the existing building and your building, and just kind of check at these different times of the year if the sun, if the existing volume in front of the streetscape or something like that blocks the sun hitting your window. You can check that really easily in SketchUp.
Sure.
If that's the case, then you can say that this is no longer a problem for me. The glare is no longer a problem for me. But if it actually, within SketchUp, if it lets you, if the sun penetrates even with the existing building, then you have a problem.
Okay.
So again, this is, we'll have to do this as an iterative design process, just go back and forth, change one thing at a time. And the other thing you had was you had an 88% visible light transmittance glass.
Correct.
You could cut that down a little bit, but that's a problem because if you cut the amount of light coming through the window, then the penetration will become a problem because daylight won't, amount of light penetrating all the way to 12 feet on the west side, you won't have as much light if you cut down the amount of visible light transmittance. So it's a balance going back and forth. So in this instance, what we could do is analyze what the blinds would do. Because right now your window treatment is none, correct?
Correct.
So we don't have to do this now, but at a later time, if you want to play with this, if you go back to that geometry input section, there's a, if you go back to that, under the window treatment, if you just click on it, it'll give you a tooltip. So you can try with B for blinds and S for shade. And then what that means is if you click that advanced options on the top right-hand corner, so here this is where you're defining what that shading device is. So blinds will be at a default negative 30 degrees rotation, and that's when it will simulate what will the blinds do for your glare and daylighting. So you can change that depending on what you think is most often the case in your office. So if it is typically closed, then you can try it at 75 or 80 degrees or something like that and see what happens. And you can change the reflectance of the blinds. So these are the specs for the blinds.
Okay.
And again, if you have a shade, if you have a Meco shade or something like that, you can try the shade transmittance, and the default is 5%, but you can change that based on your specs. So again, this is where you would change the shading part of things and go back and redo the calculation and see how shades help you overcome the discomfort glare that you had.
Sure.
Okay?
Very good.
Very good. And I will, the rest of the graphs and the final savings that you showed, I will go through that today and kind of give an idea of why you need to know that and what the purpose is.
Okay.
All right. So I don't know how I can take control from you, but can you give it to me somehow?
Let's see. Did I give it back to you?
Yeah, I think so. Oh, actually, I still don't have it. Yep, I got it. Thank you. Thanks a lot, Casey, for trying that. So in general, what did you think?
I thought it was fairly easy. The computer seemed to do the analysis fairly quickly, so you can go through and change things back and forth. I had the renderings selected too, but it still only took about 2 minutes or so for it to run through each time.
Yeah.
So yeah, I mean, it seems fairly basic, limited by obviously if you have buildings surrounding, or like you were talking about earlier, if your geometries aren't exactly just a box, but for simple spaces, I think it could be helpful.
Yep. Thanks a lot for trying that, and I urge others to give that a shot and just play with it. It's really simple. Okay, so if you don't have any other questions, I'm going to go to the next part of it, showing the lighting part. So here I'm going to start with spot daylighting autonomy. Again, I mentioned in our last class that, can you guys see my screen, by the way? Okay, take that as a yes. So we started with spot daylighting autonomy as our report type, and you don't necessarily have to change it here, but you can change to the other lead and chips in the view report section, and I'll point that to you as I go through this. So here I'm going to just create a simple room. This could be a problem every now and then. Excel will crash. So just need to, I don't know why it's crashing now. In a second. So that's one reason why we should always save it. Okay, so we'll let that go. Okay, we'll start it again. And I'm going to use spot daylighting autonomy. Okay, you say okay to that. I'm going to leave it as a pretty simple box like this for this exercise. And on the south wall, I'm going to add a really big window. Still had it 3 feet, and window height at 6 feet, window width 24 feet, transmittance 31%, window treatment none. So again, we wouldn't design like this, but this is just for an example to see what happens. So once you define your geometry, the next step is to define your electrical lighting. And here, it starts with calling electrical lighting as different arrays. So it'll start with array A, and as soon as you complete this, array B will populate, and you can add that. So for this space, let's assume that we have 3 rows of light here. So I'm going to start defining array A. So as you notice, under Luminaire, there is nothing here. So you want to go and add Luminaire. So the easy way to do this is to, during your early studies, the easy way to do this is to use a spot generic file. So under spot generic, you just choose if it's a linear fluorescent or a compact fluorescent or halogen lamps. So for this instance, I can use a linear fluorescent. So then I know, is it a direct indirect light or is it recessed fixture? So these are just default spot generic light fixtures. So I can choose Trafford lens 2T8 stands for 2 lamps of T8, or Trafford lens 3 lamps of T8. So for this instance, I'm going to use Trafford's 3 lamps instance. So once this is done, you can go back, and now if you notice, you will see Trafford lens 3 lamp of T8. And this is something that you can let this be let this auto center turned on as a row or column, but I typically like to do my math, so I leave it off. So every array, every light fixture definition needs to have a zone definition, and the zone is only to allow that light fixture to be controlled. So here in this case, I'm going to call each one of these 3 rows as 3 different zones, assuming that we would like to control each array or each row of light independently from each other. You typically wouldn't do this, but for this example, let's do this. Okay, mounting suspension. If it's a Crawford lens, recessed on the ceiling, I would mounting suspension should be 0. But if it's a pendant indirect light, then if it's hung at 8'6" from the floor, then you can, based on your ceiling height, you can give that dimension from the ceiling. So right now the ceiling height is 10. So if it's a pendant indirect light fixture, then it's typically hung 1'6" from the ceiling. So I would call that 1'6" for that type of fixture. So then the row start and column start. It all starts from the lower left-hand corner, 0, 0. So it's just a simple matrix here. So let me call this as 6 feet and 6 feet. And number of rows 1, and number of columns 3. Again, we're just defining 1 row at a time for now. But you can have an array that has all 9 light fixtures in one array. And in one zone. Again, the problem is if you have it as all the light fixtures in one zone, then you can only control all the light fixtures at the same time. You don't have independent control. So for this example, I'm going to have 3 arrays in 3 zones. The row spacing, these lights are typically at 8 foot. Actually, the row spacing doesn't matter because it's 1 row. Column spacing, these are typically at 8 feet. And orientation is actually 90 degrees, I think. So if you don't know if it's 90 degrees or 0 degrees, it's easy to check that. I'll show you how. So there you go. Those are our 3 light fixtures. So if you want to just make sure that everything's fine, just run an interactive view. So right now we are looking at the back of the classroom, which is we're looking at. It typically always shows the northeast corner. I don't know why, but that's the default. The camera always looks at northeast corner. So on the south side, you have these light fixtures going this way, spanning north-south. So I don't think that's the design of this, so I'm going to leave it at 0, the orientation at 0. Remember myself to save this often. Okay, so if I leave this at 0 and then run an interactive view again, so that's our light fixture design, parallel to the windows on the south side. So if you want to save this picture, you can. And again, the problem with this is this only allows you to save it as .pic, which is kind of a weird file format. But then you can take a snapshot if you like, or a screenshot if you want to save it as something else. Okay, so that's during your early architectural analysis, see how big of a window you need and such. Using a spot generic light fixture makes a lot of sense because that will help you go through the different iterations a lot easier. So once you have the geometry kind of figured out and make sure all your daylighting solutions work and you're contributing, you're bringing light all the way back to the classroom, and you're protecting from glare, discomfort glare, and let's assume that you've done all of that. Then it's time to put in the actual light fixture that you're planning to use. This is where you need to have coordination with your electrical designer. So let's say they have selected a light fixture suitable for this classroom. So then how do you bring that particular light fixture that they have selected? So the way we do that is to go back to Add again, and you notice here IES. IES stands for Illumination Engineering Society. IES files to library. So I can select a file. typically, this is something that you should ask your electrical designer. But here in the Phoenix office, under PHX 201, the J drive, we have a lot of light fixtures, IES files for all those different light fixtures. So for this example, I copied a couple to show how it works. So here I copied 2 files. This is I believe this is a T8 3-lamp at 32 watts each from Lithonia, I think. And notice the .ies. That's the file that contains how this light fixture will emit the light, the photometry of the light fixture. So this is very important to have. So this is exactly where we need coordination between electrical and architectural. In this example, this light fixture, I think it's an indirect direct light fixture with 2 lamps of 32 watts. So I'm going to use this as an example. As soon as I hit open, it'll ask me if I want to create a new manufacturer category and a fixture type. I'm going to say yes. So I'm going to call this Lithonia. Call it Lithonia 2 because I already have Lithonia 1. So Lithonia 2, and then I'm going to call this direct indirect pendant light. So once I say continue, then under the manufacturers, I'll have Lithonia 2. So under that, I'll have direct indirect pendant. And if I select the luminaire, it'll automatically sync in that. So if I do that, it'll bring that HL232. So if I go back to this, so let's create another array. Now you see array B. The easy, you can go through all the zone definition, mounting suspension, row start, and all that stuff again as we did with electrical lighting array A. Or we could do this copy A. Sort of cheating here, but that actually really works. So, and then all we have to do is just move the row another 8 feet. So let's say, there you go. So that puts the second array at that level, 14 feet. And again, here you have a choice of defining that as part of zone 1 or part of zone 2, or create a new zone. So I'm going to create a new zone, zone 2. You notice how the color changes here? Zone 1 is all these green light fixtures, and zone 2 is the orange color. And under zone 2, under array B, you can now select to this lighting. And again, this is not what your typical design would be, but I'm just showing you different options here. So just to make sure everything's fine, let's rerun the interactive view again. So if you notice, I didn't change the linear light fixtures position. So if I go back, see, that's at mounting suspension is 0. So that means that pendant light is actually on the ceiling. So I'm going to change that to 1.5. So now it'll be hung from the ceiling at about 1.5 feet. So let's rerun the interactive view. That's what I should see. So again, this is very critical in trying to find what fixture we're trying to use. And there's a reason why we want to go through this exercise. Because during the nighttime, the light fixture design should provide adequate design illuminance without any help from the daylight. So the light fixture design is critical for that. So going through this with your electrical engineer is very, very important. Anyone have any questions on this whole process? You can unmute now and ask a question if you have. Okay, so I take that as no. So that was pretty simple. And then I'm going to create a third array, array C, and I'm going to copy array B. So and then move that another 8 feet, so that's 22. So this is a decent distribution, and again, working with your lighting designer, you can make sure all these different spacings and the locations of the light fixtures make sense. So array C, I'm going to call that zone 3. And just for the sake of simplicity, I'm going to go back to array A and change the light fixture to that direct indirect. So if I save this and run the interactive view just to make sure everything looks okay. So that's what I should see, and that's what it is. So, and again, we're looking at the northeast corner. So the windows are towards our back, and you can change that by changing some of these gauges here. So there you go. So that's our window, a large window. So as soon as you can see this big window, we will have a huge glare issue, but we'll talk about that later. Okay, so that's facing on the south side, and let's move on to sensor placement. So while this is cranking here, I'm going to select again Phoenix, Arizona, and Phoenix. I'm going to leave everything default. And typically, this default is set up for a normal school occupancy. So I don't have any shade control right now, so I'm going to leave that as is for this exercise. Go to the next key. And if you notice here, the light fixture design that we chose, design illuminance is 40 foot candles. This is again something architecturally we have to coordinate with our lighting designers and find out what the required illuminance for this type of activity. If it's a classroom, it's typically 50 foot candles, so I would change it to 50 foot candles. And if 50 foot candles is the design illuminance, then you can ask your lighting designer what is the typical light loss factor for the light fixture type that you have selected. Based on the light fixture type, light loss factor is the amount of light that's lost during the transmission from the light from the lamp to your work surface because of the way of the geometry of the light fixture and the reflectance of the light fixture and so on and so forth. It also accounts for dirt buildup. So this is an average that you should get from your lighting designer. It is typically 0.85. So given that, now on the right-hand side, you can see during a nighttime work plane illuminance. So this is no daylight. This is strictly your lighting design that you have. So if 50 foot candles is what we want, this is the distribution that you get. So this tells me that there is not sufficient lighting from your light fixtures that you have. So this tells you that you have to go back and reevaluate your lighting design. So that's an exercise you have to go through with your lighting designer. And for this instance, I'm going to call this our design illuminance 40 foot candles just to keep things simple. So if my illuminance required is only 40 foot candles, then I'm sort of okay. I'm getting an average of 40 foot candles. So I would check this average here. It's actually quite not 40 foot candles, but let's assume it is. In your real project, you should go back to your lighting designer and reevaluate your lighting design. So with that, let's move on. It's going to do a couple of different daylighting performance. Okay, so since we have a south window, so you see that the daylight distribution here, and during clear sky, equinox at 12 o'clock, that's one thing that I always want to check. And here it seems like a really good distribution. Even at the very back of the classroom, we have plenty of light. Not necessarily 40 foot candles, but you have enough light. So any guess what our problem is? Our problem is we have a huge glare issue. But let's check that glare. At different times of the year, for instance, let's check at 4 o'clock, not a problem. Again, glare is only if you have 10 times above design illuminance. So our design illuminance is 40 foot candles. 10 times of that is 400. Anytime you see above 400, that's a problem. So equinox, it looks like we're fairly okay. But look at winter conditions. Whoa, look at that. During winter at 12 o'clock, you see we have 1,500 foot candles. So this is because the sun has a very low altitude and actually penetrates way deep into the classroom. And we have no protection of whatsoever. So that's why we're seeing this huge foot candles in the winter. At 8 o'clock in the morning, I think the sun is far low, and it's more towards the east, so we don't have that much problem. So at 4 o'clock, a little bit of a problem here on this side. So again, this is something that we have to be very careful. If your teaching wall is on that side, which is the east side of the classroom, you have a problem, because what we are looking at is the sun penetrating from the west at 4 o'clock. So you will have a glare problem at the teaching wall right here. So let's look at summer. Typically, summer schools are not there, so we might be okay. Summer at 12 o'clock, we're okay. At 8 o'clock, we're still okay. At 4, we're okay. So it's the winter conditions that is a problem. So as soon as you see this, winter at 12 o'clock, you see that much of a problem. The first thing that I would try to do is put a sunshade and see if that helps you. Again, so for this exercise, we're going to ignore the fact that we have a glare issue, but you should address that in your real design. So if you look at view report, spot daylighting autonomy. So it wants you to reevaluate your design, and the reason is too much direct sunlight or exceedingly high daylight illuminance. So we know why that's a problem. That's because of this max DA. But if you control that max DA, which is the metric for discomfort glare, if you control max DA, then look at your daylight saturation, which is the amount of light that gets penetrated into the building, into the classroom. So that's about 60%. So that's a very good design. And again, this is a lot of windows for a classroom. But if you treat the window with proper shading solutions, then this should be a really good design. Okay, so now let's go. Here, I just wanted to point it out. You could change the different metrics that you want or reports that you want to see. For instance, if this is a LEED project, then you can do LEED single point calculation. It will ask you, will glare control measures be used for this space? You have to say yes, because that's a requirement for LEED. So, and again, by saying yes, you would take measures such as controllable blinds or something like that. And then if you continue, you notice here direction control pass, everything's passed. So achieving for LEED, it asks you to check if you have 25-foot candles at the work plane. So here, 100% of your work plane has 25-foot candles. So according to LEED metrics, your design satisfies the LEED daylighting credit. Again, LEED asks you to make sure that you control glare. So if, for instance, if collaboration for high performance schools, if that's your metric, then you can do one of these. You can do the single point calculation right here. It'll take a second. Again, the same glare control, daylighting controls. So here, if you go down, your evaluation, you pass. So if anybody is using chips, they can still use this program to evaluate. And you can actually submit this report as part of your calculations. Even for LEED, you can. Okay. Just going back to our design here. So now this is run. So we can go next. So this is where we're starting to define our sensors. And typically in a room like this, in a classroom, at best we'll have one photocell. But for this instance, I'm going to show you that we will have 3 photocells. So for every zone, Spot will automatically come up with a sensor. It's up to us to define that. So for this example, I'm going to assume that we have 3 sensors. And the more sensors you have, the better the chance to harvest daylight, because you can control these individual zones much in a much fine-tuned version. So again, this is something that you have to coordinate with your electrical designer. I typically just use the Lutron photocell, but again, this is something that you have to check with your designer to see what he's intending to use. So I'm going to select Lutron for all 3 of them. So as of now, so on the right-hand side, if you see these are my arrays, lighting arrays, and photosensor. I don't have a photosensor located yet. So I want to tell it where to put the photocell. It typically is in the ceiling. So I'm going to call it C, and you can follow the tooltip here. Other than C, these mean it's on the walls. Southwest, northeast is on the walls, but it's typically on the ceiling. So once we put that, and so here, if our designer knows where to place these light fixtures or photocells, we can give an XYZ coordinate for all of them manually. But right now, you see that all of them are in this location at 10 feet at 0, 0. I can change this to, let's say this is the sensor 1. I'm going to use sensor 1 for this first zone. So I'm going to call this, I can go ahead and type it at 6, 6, 10. So you notice how it moved. So I can move it maybe further down, 10, 10, or 10, 6, 10. So it'll be right in between these two. So this is one way to do it. The other way to do it is to allow it to auto-generate. Again, I'm going to save it. So this will actually take some time depending on the complexity of the geometry. So it's going to warn you that it will take some time, but it won't take an hour though. It will go fairly quick, probably a couple of minutes or maybe 3 minutes. It will actually go through every single light fixture array and cross-correlate the sensor's location with that light fixture array. And at the end, it will give us the correlation. It will tell us what light fixtures, or what zone, or where do you place the sensors to get the most out of daylight harvesting per zone. So that's the correlation we can see here. So this is going to take some time. Typically in our classrooms, at least in the last few jobs, we've had only one sensor located close to the window. So our window's on the south side, one sensor located close to the window, and the additional electrical light fixture arrays or zones will be controlled based on an algorithm. So, for instance, if this light fixture array sees enough light, so it says its light fixtures that it can turn off 100% of all of these lights, then we can program an algorithm to turn the second zone or array B, this row, to maybe 60% down, and then the third row to be maybe 30% down, depending on the daylighting penetration design that you've come up with. So that's one way to save money and save complexity. The more number of zones you have and more number of sensors you have, the controls become a problem, and you have to calibrate them periodically. So that's something that we've done in the past, is to just do one photocell and then control the other rows using a program, using an algorithm programmed in the lighting control system. even though it says warning, no light sources found, ignore that for a second. All right. So Spot automatically found these 3 locations that's what is ideal for controlling these light fixtures based on the window design that we have. So this is the recommended location for these sensors. Again, we as a designer, we have the option to rule that and put it in a different location. But this is the recommendation from Spot. So if you notice here, zone 1, if I want to control that with sensor 1, you see, if I hit view correlation, I have about 20% correlation. The higher the correlation, the better. So if I change this to zone 2 and view correlation, something doesn't make sense. So actually this tells me that zone 2, which is that zone, so having the photocell located here for zone 2 is more, that makes more sense. We try zone 3. I have to get back on this. This doesn't make any sense to me, but I have to get back on this. This is just an idea to understand how these things work, but this wouldn't impact our design. I'll get back to you on how exactly to interpret this. But for now, I'm going to move on, and we'll go through further calculations. So this is the point where it actually tries to figure out how much percentage of light that I can turn off depending on the daylighting availability. And then in the next screen, it will give us an option to choose what type of what type of controls we have, whether it's a dimming control, continuous dimming control, or whether it's a step dimming control, or whether it's just on-off. So far, any questions, anyone? You can use the chat function if you have a question also. And for the guys in the other offices and Phoenix, I will shoot you an email with the location of all these different light fixtures, IES files. So if you're working with a consultant outside of DLR group, then you can just ask what type of light fixture it is, and you can find the IES file from this database. We have an extensive database here in the Phoenix office. I know we're getting close to the time limit here, but I just want to quickly show the last two screens, and that'll be the end of this program. Starting maybe next week or the week after, depending on everybody's schedule, we will start eQuest. That's an energy simulation program. It's a pre-program as well from the Department of Energy. So we can use that for initial pre-design stages and schematic design stages, and even for design development and construction document level detailed analysis. But we're going to look at how to use that program during schematic design and pre-design stages. So just bear with me here. It should be done pretty quick. All right, so if you go next. Okay. The current signal bandwidth is too small. Again, this is where it gets really technical, and I would suggest that we check with our lighting designers and lighting control designers to help with this aspect. But in general, signal set point low and high, these are something that are very technical that we probably need to get some help from our lighting designers. But here, this is a place where you can again define a Lutron ecosystem. That's the type of sensor that I chose. And continuous dimming will give us the best daylight harvest savings than any other dimming method. The ecosystem is a continuous dimming system. So if you had selected a different light fixture, different photocell on the previous section, you will have different options here for controlling that. And here, all it is trying to tell us is the work plane illuminance for each zone. So if I go down here, I'm going to make this go small. So this is the controller image of how the controller will work. Again, we don't need to know that. So we can start viewing different correlations here. Minimum correlation and then the average correlation. Oh. Okay. Okay. So work plane illuminance. So these are in foot candles on the left-hand side, and these are the photosensor response. And you notice how during sunny conditions, that's the minimum correlation of how the sensor and the how the sensor correlates with the amount of daylight that's available. Again, do we need to know all of this? Probably not. This is something that gets really technical, and I think I have some problems with the bandwidth here. And this is something that depends on how much we set our signal set point here for low and high. This is probably where you need some help from your electrical designer in trying to help define this. I would again not have a lot of different zones and different too many lighting sensors, photosensors. If you have one sensor, it typically doesn't give you as much problem. It automatically figures out the low set point for you. And I have to do some digging to find out how to fix this. But in general, it doesn't allow us to go further out because of that problem. Yeah. So, anyways, running out of time. Maybe we want to spend one more session on this specifically for our lighting designers. If I can get more information on how to use this, but architecturally speaking, work with the lighting designer on this part. And since we don't have this figured out yet, it doesn't allow us to do the dimming calculations. Well, once we clear that and go back and reduce some of our sensors and try to figure out the signal set point, low set point, it'll go through, and the next screen should be it'll tell us how much electrical and lighting savings we could have. I'm sorry that I couldn't show that part to you because of this issue. And again, we're running out of time, so I'm going to conclude this for today. So maybe we'll have one more session on this. Again, please unmute and tell me what you think. Do we need to get into this detail on the sensors side? I'm looking for some feedback from you guys.
Hey, Prem, this is Mike down in Tucson. I don't think at least not for us down here. I mean, getting into that much detail on the lighting is probably not a big deal for us down here in Tucson, but we also don't have the electrical engineers like here in office either.
Okay.
So that's usually something that, like, for example, the 2 projects we're working on right now are both outside engineers, so they take care of most of that stuff themselves.
Right. In that instance, what I would suggest is, at least from a daylighting standpoint, you could still use this and use generic light fixtures and see if it works with your design.
Yeah, and even though it didn't work in that one space I tried it in, there's some other spaces in, say, some of the projects we could still, I could still use it and just do a basic analysis of some spaces that we're actually having some questions about putting some solar tubes in for extra daylight. So.
Okay. You can simulate a solar tube as a light fixture. If you go to SolarTube's website, they will issue an IES file, .IES file for the solar tube. So that'll be easy to simulate that as opposed to using it as a skylight.
Okay. Yeah, we'll do. All right. Well, it's very. I thought it was pretty informative, Prem. So thanks for doing that.
Yep. You're welcome.
All right.
All right, guys.
I'm gonna let you go. I'll talk to you later.
Okay. Thank you.
All right. Bye.
All right. Thank you, guys.
Thank you, Prem.